I'm Megan Lane. I'm the community director here at RISC-V International. I'm really excited to talk more about the hackathon presentations that we're doing with students. We held our first hackathon at RISC-V Summit Europe, which was really well attended, as well as this one. So this is sort of a collaboration between our member organizations who are interested in training the next generation of RISC-V engineers. So the students on Monday had from 11:30 till 6 p.m. to work on different hack projects from our members, and these are the corresponding presentations they came up with that. We asked them to do one slide. A few did more than that, but I was impressed that some of them were able to do it with one slide because I cannot do one slide. So if you are a member organization and you're interested in participating in these in the future, please do let us know. We're also looking at partnering with other organizations such as MIT and High Peak Conference. So we're excited to have more of these opportunities for students to have these hands-on learning experiences and working with our member organizations. So we're going to skip that one, they're not here yet, and move on to Codasip. So they will first present what the problem was, and then the students will come forward with their solutions.
Okay, thank you, Megan. Just give me a second here. Okay, so my name is Tadej. I'm from Codasip. I'm an innovation engineer over there. And our challenge for the hackathon was to use our tool called Studio to extend a CPU and make it hardened for radiation. I'll go into more specifics later, right? And the goal is to make the CPU survive interstellar space, where it is bombarded with alpha particles, which flip individual bits in the register file. So the motto of Codasip is custom compute and architecture efficient, but we changed that a little bit for the challenge, and we call ourselves Cosmic Compute Incorporated, because we're, doing computation for satellites. And the idea is very simple. While in a real system, right, radiation hits everything, including the memory and the combinatorial logic. But for this specific challenge, we've only kind of focused on the register file. And we've created a system in our tools that corrupts the register file randomly each cycle. And that corruption gets more severe as the time goes on. And the goal is to extend the register file to include some ECC algorithms, some convolutional codes, whatever, to encode, decode, and fix the register file, and try to get as far as possible. So Codasip Studio is a tool chain that enables describing, developing, and customizing his CPUs. Basically, we have our own language called Codal. It's basically C. You describe the CPU, how many pipeline stages, what are the instructions, and whatnot. You press a button. On one side, you get the RTL. You press a button. On the other side, you get the compiler. We didn't bother with the compiler for this challenge. It was only the only challenge was to extend the register file to do the codes needed. And as I mentioned, the goal is to get as far as possible while the severity of the radiation gets stronger and stronger, right? And hopefully, right, you can get to the galaxy far, far away and meet Yoda. And that's basically it, what the challenge is all about. Thank you.
Good afternoon. My name is Luke Lomas, and I'm a first-year undergrad at Columbia Community College. I chose to work on the Codasip project, doing the ECC. I ended up trying to go for a Reed-Solomon algorithm. I spent countless hours racking my brain trying to get Lagrange interpolation going so I could encode it. Sadly, I was not able to get any successful attempts, being quite underqualified for this. My goal was to have at least 3 errors before it all fell apart. You can see here that that's what I was able to get written. Thank you so much. It's been an honor.
All right.
Hi, my name is Swati.
My name is Chloe.
And we both go to Berkeley. And this is kind of the scheme that we wanted to implement to solve this problem. So we wanted to implement a Hamming 3832 encoding scheme to detect up to 2 errors and correct single-bit errors, like those that may be caused by radiation. I think we decided to use a Hamming scheme in the beginning in order to minimize the bits the extra bits that we'd be using, because in this case, because we had 8 registers of 32 bits each with a 38 bit scheme, we'd be able to get 48 extra bits, which is still, a good amount of extra bits, but it does reduce, it reduces the problem, and it has less compared to some of the other schemes like Hamming 7.4 and like the triple redundancy and the quintuple redundancy, which is why we tried to go for like a scheme that would reduce the number of bits added to the register file as much as possible. Do you want to say anything? Okay. Anyway, so yeah, just talking about the limitations first is just it's effective for single bit error correction, but it's not as good as in handling burst errors or multiple errors beyond a single bit, which is why we also discussed, although we couldn't fully finish the implementation for those, we also discussed working on interleaving, and we also discussed maybe using Berlekamp-Welch and using a polynomial to encode our quote-unquote secret, or encode the points. But we also would need to know the amount of errors for that in order to design an error polynomial, which is why we decided against going that route as well. And then we are going to also explain a little bit about how both of our functions worked. So,
okay, so for our first function, we have decode and fix, which is the actual decoding of the Hamming function. And it calculates the syndrome by calculating the parity bits, checking the parity bits against the given data bits. If the syndrome indicates an error, the function would identify the specific bit position error and mark that as needing to be correct and flip it. And then after correcting any detected error, it would extract the original 32-bit data and assign it to the proper value for further processing.
And as in this part, we talking about our signal management. One thing that we did want to do was improve our signal handling, but we use signals to hold some of the intermediate parity values to manage and update the values more efficiently as well. And then we also introduced a couple signals to act as error flags to indicate whether an error has been detected and then corrected in each register, and that would allow the other pipeline stages to react and process accordingly in a way that's easily communicable. And then talking about our encode and insert function. So this function encodes a 32-bit value into the 38-bit Hamming code when the write enable signal is active, and then we place the original data bits in the appropriate positions of the 38-bit code word, leaving the space for the parity bits. And then the fully encoded 38-bit Hamming code was then prepared for storage in the register file through the signals. Yeah, and then that's kind of what I think we talked about, some of the future improvements that we would have liked to do before, but yeah, we were able to, use less extra bits than some of the other schemes that we discussed, and we were able to extend the number of clock cycles by a little bit, but not by as much as we would have liked, which is why I think it's important to also think about the trade-off. Do we want more clock cycles at the expense of more bits that can keep getting corrupted as it keeps getting extended? And we personally chose to go for less bits less bits being used and less clock cycle, just because part of the problem is the fact that as it keeps going, it gets more and more corrupted, and that means with more and more bits, more and more things can get flipped, and in that case it becomes exceedingly harder to recover, which takes longer time and just becomes less efficient overall. So we kind of chose a simpler scheme in order to maximize what you get out of it, if that makes sense. But I think there are a couple more things that we definitely could have done to improve it. But I think like we would love to do that if we had more time. So yeah, I think that's about it. And thank you so much for the opportunity to do this project. We really enjoyed learning. We learned like so much, and it was really cool to use this language too. So thank you.
Hi, everyone. Hi, I'm Nikhil, and yeah, this is my solution for the Codasip problem. Okay, so what I tried to do was a very simple Hamming code solution. I just did the 7 for Hamming code, mainly because I was kind of confused with the simulator environment. I feel like when I was doing like complicated solutions, the simulator kept timing out. Like it wasn't able to solve it. Maybe I was doing something wrong. I wanted to aim for something like Reed-Solomon codes, like polynomial division, but this is what finally worked for me. So yeah, so it's pretty simple. It has 3 parity bits and 4 data bits, and these are the encode and decode logical equations that I used. It's just calculating the parity, and whenever there is a correction in the data, you just whenever there is an out, like whenever the parity doesn't match, you just correct it by using the following equations. That's it. So yeah, it achieved around 1-bit error correction per 4 blocks of data, which and for every 4 bits of data, it used 3 bits of parity. So yeah, that's what I did. Yeah, that's it. Thank you.
Oh, hello everyone. So I have read about some algorithms and solutions for the problem, and I try to do something simple that works and worked. So I have my register of data, and I'm saving a copy of this register, and I'm saving a 30 register that I call it padded bit register. I'm dividing the register in the middle and doing a XOR operation in the middle and doing like this one with this one, this one with this one, and saving the results in my padded bit register. So I know what bit should be there. And after that, it was the encoder step. I have my decoder step. So I get my register, and I do an XOR operation with the copy of the register that I have. And I expected that this operation returns 0 if any bit flipped, but if some bit flipped, it should return some bits 1s. And if it returns a bit 1, I have 2 possibilities. The first possibility is my register of bits, one of the bits of my register flipped, and the second possibility is one of the bits of the copy of my register flipped. And to figure out what happened, I can use my padded bit register. So using the result of the first step, I can do some logical operations to confirm if the bit of my original data flipped or not. And if the bit of my copy register flipped, it doesn't matter. I'm just fixing the errors of my original register. So I have my padded register that has the information about, for example, that XOR operation. And I can perform that XOR operation again and compare the result that I had with the new result. And if the result is different, it means that it flipped. And if it flipped, I know in what position, and I can flip it again to restore the original data. And I have run it, and that is the results that I got. Thank you.
So I'm just gonna tell the proof of concept for the idea that I came up with. So we had 8 32-bit registers, and the idea that I chose was like we could split it into 28 bits and leave the last 4 bits. And for the first 28 bits, we could split them into 7 bits each. And I found an algorithm called the BCH157. What it does is it takes in 7 bits as input and it gives an output of 15 bits. It encodes them and gives an output of 15 bits. So, and the another benefit of using this algorithm compared to the ones which were given to us, the Hamming one and the other algorithms were, this could detect 2 errors at a time. So with the encoded 15 bits, we could not only detect 2 errors, but also this algorithm could correct them. So I was applying BCH157 algorithm to the initial 20 bits. So they were divided into 4 segments, 4 into 7, and the 4 segments were applied BCH157, and the last 4 bits I applied the TMR algorithm, triple modular redundancy, that we already it was given as an example in our document. So what it does is for each bit it additionally adds 2 copies. So the benefit of this algorithm was that the total number of bits required for one complete register is 60 bits, and the total for like 8 registers, it requires 576. This is a lot less compared to TMR and QMR. TMR requires almost 768 bits, and QMR requires 1280 bits. And the Hamming code requires less bits compared to BCH, but the benefit is Hamming can only detect 1 error, while BCH can detect 2 errors, so it increases the probability of finding an error. So compared to both of these, I feel like it can be proved that this will be more efficient. Yeah. Thank you.
Hello, everyone. My name is Mubar JJ. I'm with Tactical Computing Laboratories. We hosted a hackathon during this summit on Monday for a solution for the memory wall, which I'm sure we're all familiar. But for time, I'll skip some of this more interesting graphs for the actual hackathon itself. The participants were instructed to offload subfunctions of a shortest path algorithm called A* to a PIM device, a processing in-memory device. And the purpose of this project was to help participants to get more knowledge on SST simulations as well as REV-SST. REV-SST is a simulated RISC-V processor based off the simulation toolkit provided by Sandia National Labs. It's the only parallel discrete event simulated processor for RISC-V on the SST toolkit. Oh, here we go. So we helped participants walk through this hackathon by going through a series of tasks. The first task was to use the A* source code provided to them in the resources that we provided, and then compile that for their host system, just so they were familiar with how the program is supposed to be run. That was followed by editing an actual RISC-V machine in SST. This required them to edit the L1 cache, the L2 cache, the memory controller, memory, and of course Rev, the RISC-V processor core. While we did provide some templates for these configuration, it was really up to participants to write in the actual parameters themselves and read the documentation for SST as well as Rev and these other submodules. Now, after they did a run of SST using just the A* program in software, compiled by their RISC-V compiler on their host machine, they were later instructed to offload some of those sub-functions to the PIM device, which we provided that connects directly to the MEM controller within the SST simulated machine. The PIM device came with 3 different hardware functions, were meant to be exact parallels to the software functions used in A-Star. Now, of course, these hardware functions are going to be more specialized. You're going to get a faster or less cycles to run the actual program when you offload these functions to PIM. But the purpose of this hackathon was to ask participants to walk through the process that I at TCL do quite frequently in microarchitecture design, and make connections and relationships between the performance metrics that are pumped out from SST to the configurations and parameters that they set earlier in the hackathon. So I'm looking forward to these presentations that are coming up, and I'm glad that this was my first hackathon that I wrote here for the RISC-V Summit. So thank you very much.
Don't tell the events team that we're plugging in and plugging laptops. They would be disappointed in me. That was awesome. Thank you so much for introducing that. So I also want to say that Tactical Computing Laboratories paid for lunch for the students, which I don't know if you remember being a student, but free lunch is always a draw. So, and they're nodding their heads. They're like, yeah. So thank you for that. It was really helpful. So now I'll let these presentations go on.
Hello, everyone. My name is Shuqi. I'm from UC Berkeley. One fun fact about myself is that actually I'm enthusiastic about developing next generation computer technologies, and I've been developing quantum computing technologies because I'm a PhD in physics. But since I took 621C at UC Berkeley, I feel that RISC-V is really interesting. That's why I'm here. And joining this hackathon. I think the format has screwed up a little bit, but I think it doesn't matter. So it's my pleasure here to introduce my solution to the TCL Hackathon Challenge. Basically, this hackathon is about evaluating the performance of a simulated RISC-V machine with and without a PIM device. And this hierarchy has been shown in the introduction of the problem. Just quick walkthrough of the configurations we use. We use a single core RISC-V CPU, and we have a memory hierarchy of L1 cache, L2 cache, and the main memory without the PIM device, and also the controller to control the memories. For the L1 cache, the delay is 8 cycles, and the L2 cache is 30 cycles, and the main DRAM memory is 100 cycles. But yeah, it's big, set to 496 gigabytes in the simulation. And for the L1 cache, it's 16 KB, and 4-way, and for each cache line size is 64 byte. And when we add the PIM device, it's located like isolated from the rest of the memory. It's directly communicating with the CPU without going through the caches. And for the PIM device, it has 1.1 KB of SRAM and 390 KB of the DRAM, and also some predefined functions inside it. So the next is to simulate some useful functions on this machine. And there's the provided test bench is about A-star search on the shortest path from source to destination. The first step is to use the linear feedback shift register to generate 512 pseudo-random numbers as a seed for the random distance between the nodes. So that means that there are a total of 512 nodes, and this number is correlated to the set of the L1 cache. So L1 cache has like for each set of L1 cache, it can store 512 of in 64, and there are 4 sets of them. So it's not a lot. The second step of the test bench is to use symmetric distance matrix generation to create distance between 2 nodes. So that means the matrix size is of 512 times 512. That's allowed because you can only store 4 times 512 in the cache. So there will be a lot of cache miss and a lot of memory waiting time inside this step. Another thing about this is that it uses 2 nested for loop to scan the dimensions, and inside the for loop, it assigns both the symmetric position of the matrix, and because a matrix is stored either column major or row major, so that means there's only one fashion that can take advantage of the L1 cache, and the other fashion would continuously evict cache and then pull memory, pull data from main memory. So that makes the second step the most time-consuming part. And the third part is about A-star search for the shortest path given source and destination node. And the default setting in this algorithm, it doesn't use any heuristic, so it just scans all of the possibility. And after implementing the PIM device, we compare the performance to the performance without PIM device. We can see that for the total computational time, it's 10 times faster. And to look closer, we can see that the bytes read from the CPU is 56 times less than without PIM. That means there's a lot less data being read to the CPU, and also the CPU read in flight time is 55 times less, so a lot less time spent in the memory waiting, data waiting time. And for the L1 cache, we can see that it is being used the miss is about 766 times less, and that's not. So this last row is about the hit rate. So it's actually similar. This without PIM is 68%, and with PIM is 60%. So that means the cache misses is now optimized through more cache friendly algorithm or something like that. That's improving the hit rate of the cache. It's fundamentally reducing the the queries for the cache. After looking at the numbers, we can give some conclusion on this PIM advantages and disadvantages. For the advantages, we can definitely see that the latency is of the data transfer is minimized, and also the energy consumption of the data transfer is also minimized. And another thing is about this advantage I didn't put here is that there's some computational parallelism happening in the PIM device. And that's also saving a lot of computational time. So when I try to play around with the parameters and set the delay cycles to 1, and I still find that the total number of CPU cycles is about 3 times, is about 3 times of this number with PIM device. So that means there's a lot of computational parallelism happening in the PIM device that boost this computational performance. And lastly, I think for the future, hardwares, there's an inevitable more memory wall happening. So that even makes the gain from using PIM device even larger. But there are definitely some trade-offs by implementing PIM device in the hardware. First is there's more overhead to manage hardware definitely is more complicated and it takes more area. And also like the functions you define is not universal. You have to tailor it for like application-specific algorithms. So I think probably implementing more functions would be like would kind of kill the advantage a little bit. Or I'm not sure how many functions is possible being implemented here actually in the hardware. But yeah, definitely it won't be a very universal solution. And another thing is that coding the algorithm on PIM device, it's different than coding for other hardwares. Like we see at the moment, CPU, GPUs is probably a little bit similar to GPU, but not exactly the same. So that means there's more software need to be built from the scratch, from the very low stack and all the way up to the applications we are using right now. So yeah, that's the conclusions I have, and thanks for listening.
Hey, hello everyone. I'm Shivam, and I also worked on the same problem where we are trying to use PIM to eradicate the memory wall. So I would say my solution is broken down into maybe mainly two pieces. One is actually implementing PIM and seeing the overall benefit of it, but there is also some amount of analysis, where we try to figure out that, hey, where exactly was our memory bottleneck, and of all the functionality that I have in the given program, which particular part would it help to accelerate with PIM. So just to give a intro of why PIM and where exactly it helps. So the first line says that for many kind of applications, especially nowadays with AI, CPU caches end up fairly small. You have very large working sets. You have to load huge matrices in the memory, and the CPU caches are not really enough for that, which ends up being bad locality, lots of evictions from the caches, lots of write backs to the memory, and in the end you end up consuming more memory bandwidth, which slows down your application and also increases the energy cost of it. So with PIM, the idea is that we try to offload at least some part of the compute to the memory, at least maybe the simpler stuff that can then help accelerate the applications. Right. So yeah, I mean, I would first start with how the program works. So we are doing the A-star algorithm here, where there are 3 steps. So first one is linear feedback shift register, where we mainly operate on a 512-bit vector. The second one is building a symmetrical distance matrix, where we have 2 or 3 for loops which are embedded within each other, and then we are trying to build a matrix. But the way it is coded is by design inefficient in a way, because the authors wanted to show how caches are not ideal for this. So the way they allocate the matrix is on every last iteration of the loop, we allocate the matrix R, C and C, R, basically both the diagonal elements in the single iteration, which means it would face this bad locality, and every time you have to actually write back elements of that matrix to the memory, you would end up having to evict it from the cache. So that's the second function. And third one is the actual A-star algorithm, where given the results of the first 2 stages, LFSR and the symmetrical distance matrix, we run the actual pathfinding algorithm and try to find the shortest path. Yeah, I think we lost the header for the first graph here, but this graph tries to profile the 3 functions that we have. So to do the profiling, I have sort of set up a proxy profiling flow, that instead of, I think SST also has a profiling infrastructure in place, but I did a more simpler thing where I now have to run 3 functions which are dependent on each other. So we just run, say, the first one at a time, then the first and the second, and then all 3 together, and then you can just get the delta between these runs to get an estimate of how much each stage is using in terms of your caches and the memory. So that's the proxy profiling flow to get these numbers. And this graph, I'll just mention the titles because they are kind of hidden. So the first set of 2 bars is the LFSR function, linear feedback shift register. The second one is building the symmetrical distance matrix. And third one is the A-star function. And the left axis is where we plot the number of L1 cache hits and misses. and the right axis is for the line where we plot the total cache accesses, which is nothing but the sum of the first two numbers. So what we see here is the symmetrical distance function is the one where we spend most of the memory access bandwidth. Because like I said, we do this allocation of diagonally opposite elements, and that ends up thrashing the cache. So this one, if you see the number of misses are very high here. Misses is the black bar, and although the number of hits is also high, but you also have to end up writing that back to the memory. And talking about the size of the vectors, this in the symmetrical distance function, the distance matrix that we build, it's a 512 by 512 matrix with each element being 64 bits. So that's a 2 MB, 2 MB data, which doesn't really fit in the caches. I think we had the system set up in the previous slide, which is similarly followed here, where we have only a 16 KB of L1 cache. And in the other two functions, we have relatively smaller variables, which are only 20 KB in size. So this set of graphs is when we go to the very ideal case, where assuming that the PIM device supports all the functions that you need for this algorithm, and all of that runs on the PIM device. So the only stage where the CPU is involved is the first time where it allocates the memory and writes it back to the PIM device. So the first graph shows the total cycles, where we see that it has drastically reduced by more than 10x. And then there is a breakdown of each of these functions, where the symmetrical distance was already the highest, and that itself also reduces by about 9x. And the runtime gains are relatively smaller on LFSR and A star. Then going for the number of bytes read, now you can see that the LFSR and A star both have almost negligible memory accesses compared to the symmetrical distance function. And it now sticks, because at least in the first iteration, you do need to read that from the CPU and then write it to the PIM device for it to actually operate. And the last one is the number of bytes written, which is where we get the most benefit. So if you see the symmetrical distance function, that has now almost gone to 0 from its initial stage when it was only running on the CPU. So the intent behind getting this breakdown across multiple functions was basically this idea that in PIM, it might not be possible to dispatch every single function, right? I mean, if you just support every operation, then you're building another CPU. So you do need to have that, basically that balance where you support the minimal possible thing on the PIM device and try to get the maximum performance out of it. So this last table tries to show that breakdown, where what if I did different stages on different devices. Right? So the first row is where we do everything on the CPU, which is our baseline here. And the second is where we do everything on PIM. So of course, this second case gives the best speed up, where it is 90% faster than before. So when I say speed up, I am just taking a ratio of the total cycles. So with everything on PIM, it is 90% faster. You almost do not have to use the cache, and you reduce a lot of the memory bandwidth. But like we saw, the symmetrical distance function is the biggest bottleneck. So if we just do that on PIM and the other two on CPU, even then we are able to get 81% speed up, which means now your PIM device needs to support only one function, and still you are getting an 80% speed up, which is a great trade-off, I think. Yeah, that's all my solution. Thank you.
Hello, everybody. So we are really happy to be a member of the hackathon. We had a few hackers participate in the Andes portion. The Andes hack was to use our AX45MPV, that's our vector processor, and our ACE tooling. ACE is Andes automated custom extensions. That's how our customers add instructions to a processor. And we have a lot of customers doing AI with our processors. So we wanted to present our hackers with a real-world problem that a lot of our customers actually face every day, and that is how to optimize nonlinear functions in the RISC-V processor. So our hackers tackled optimizing a softmax layer, which is useful in a lot of neural networks, including LLMs, using vector processing and our ACE functionality. And so we had a presentation prepared by Iana Lim, who apparently is not here. But our hackers worked as a team, and I'm happy to present Kevin Kim from the University of Waterloo to present his solution. And also thank you, Kevin, winner of Andes-powered wireless gaming headset.
Thank you.
Right, so on behalf of Iana Lin, Ethan Gao from Berkeley, we kind of worked on it together to implement softmax function, the common activation function used in many neural networks at the last step, but also throughout the entire pass flows in transformer models. As you may know, just some background, softmax is an input vector of scalar elements that have to be, that undergo natural exponentiation and are normalized by the sum of all elements. And so how can we optimize this? So what are different ways we can optimize this? So thanks to the technical team at Andes, Hubert and Joseph were able to provide us with a modular image that got the development process jump-started. Our task was to implement C-based functional behavioral model that, with the use of the ACE tool, automatically generates RISC, RV vector extension intrinsic functions. And so, optimizations. Firstly, we looked into vectorization. Each of the exponential operations and summing and division, these can all be vectorized and parallelized in hardware using the RV-V extension. This was using their flow specification in C functions and running their Copilot tool. It allowed us to kind of automatically generate the necessary assembly instructions that follows. Next, as you can all imagine, natural exponentiation is a very computationally expensive and nonlinear process. And so aside from defining constants to merely approximate e to the x, where x could be, say, like a float 32, which was our default data type. We took Taylor approximation approach, the approach to approximate that computation using Taylor series approximations, which would enhance accuracy. So not much to show technically here, but even just the XPF function from the default math library in C, which is implemented using internally some sort of polynomial approximation, did give us an accuracy boost in the tests that were run, where the vector lengths ranged from 3 elements to 71 elements to 2048 elements. Another optimization that could be explored is numerical stability. So handling an overflow and underflow in flow 32 can take up additional cycles. And so to avoid that, we kind of offset each element using the max value of all the scalar elements in the vector to kind of prevent that scenario. As you can imagine, the range of values that we can get from flow 32 are exponentiated, can only take the range from like 87.6 to negative 87.6. Not a great range. And so that allowed us to also increase number of cycles that were reduced in the test run. Another optimization, that process involves finding the max element within the vector, which implies that you require one additional pass through the vector to find that max value. So there's some papers that kind of optimize upon this, which we weren't able to implement, but they exist out there. This softmax has been around for several years. Another approximation approach could, from an NVIDIA paper, was replacing the base of E to 2 and some additional fine-tuning at the end, but without that latter fine-tuning, just that mere approximation did not yield us too much of an accuracy boost compared to the just default approach in defining constants for natural exponentiation. Another optimization approach we looked at was different areas in code that could be further parallelized in hardware. So we have several for loops that all increment using just an index variable. And so one thing that you could do is actually create a custom vectorized function that increments the index loop for all the for loops that exist in your computation and vectorize that so that they are all incremented in sort of SIMD fashion. That will reduce latency and other some last optimizations we looked into. I think that was all that we were able to cover. Obviously, not too much to show technically, but thanks to Andes, they had the whole build flow, the make flow, and test results reporting, which we were able to simply just have execute a shell function, and it all automates this process, including the assembly instruction generations. So yeah, thank you to Hubert, Joseph, technical team, and yeah, thank you.
Oh, here we go. Well, thank you to all the students for presenting. If the students want to come meet over here, we have some individual prizes to give away. And then if anyone has questions, feel free to come ask. And we're just really grateful for everyone's participation. There's a lot of hard work that goes into this, from the organizations that are providing problems to the students just dedicating time and probably skipping school. So thank you, everybody.